Welcome back. So today we're going to look at some more PRAM algorithms, and we're going to look at algorithms on graphs. So the first problem we're going to look at is about coloring a cycle. Okay, so for the coloring problem, we're given a graph G. And then if we want to k-color the graph, then that means that we want to assign every node a number, okay, between 0 to k minus 1. Okay, so one of k possible numbers. And we want to make sure that the number for any edge in the graph ij, we want to make sure that we assign different numbers to I and j. Okay, so today we're going to look at how to color a cycle. Okay, so this algorithm is only going to work on a cycle graph. Okay, but we're going to see that this algorithm is very, very fast. And furthermore, even though a cycle is a very special type of graph, it turns out that by coloring the cycle, we can actually use this algorithm as a subroutine in some other important algorithms. Okay, yeah, so we're going to look at a super fast algorithm for 3-coloring a cycle. Okay, usually we're trying to minimize the number of colors that we use. And we can see that in the case of a cycle, if we have an even number of nodes, then it's possible to color the cycle using just 2 colors. Okay, we just alternate between the colors. However, if there's if the cycle has an odd number of nodes, then we have to use at least 3 colors. Okay, so we're going to give an optimal algorithm in terms of the number of colors, and this is also going to work very fast. Okay, now coloring the cycle is a form of symmetry breaking, in the sense that if you're given a cycle, then initially all of the nodes think that they're the same as any other node, right? Because there's nothing basically to differentiate these nodes initially. Okay, except that we're going to assume that these nodes have different IDs to start out with. Okay, and all of the nodes have different IDs. So initially, the only difference between these nodes is their ID. Okay, and then we're going to somehow make use of these IDs so that eventually the nodes end up with with these values, with these colors from basically from 0 to 2. Okay, so every node gets one of 3 different colors. Okay, now for each node v, we're going to let S of v be the node that comes after v. Okay, so the successor of v. All right, so now the way this algorithm works is that initially, since we're assuming that these nodes have IDs, then every node is going to get, the color of each node is simply going to be its ID. Okay, and then since all of the nodes have different IDs, then initially for any edge in the cycle, right, the endpoints have different colors, okay, because they have different IDs. Okay, so now this algorithm is going to work in phases, okay, or rounds. And in each round, what we do is that, well, we assume that we start with a valid coloring, okay, meaning that for each edge, the endpoints have different colors. And then in this round, what we're going to do is to reduce the number of colors that we use. Okay, so for example, if you start the round using like 100 colors, then after the end of the round, we want to use something like 10 colors. Okay, so that's the basic idea. We keep reducing the number of colors we use until we're down to like 3 colors, and then the algorithm terminates. Okay, and so the way we do this in each round is that we're going to look at the color of each node v. Okay, and we're going to look at the, so let's denote that by C of v, right? So that's the color of v at the beginning of the round. And we're going to look at the binary representation of C of v. Okay, and then we're also going to compare. We're also going to look at the color of the successor of v. Okay, and its binary representation. And now we're going to compare these 2 binary representations, and because v and C of v, v and its successor have different colors, right, then their binary representations has to differ in some bit. Okay, otherwise they would have the same color. Okay, so there is at least some bit where they differ, and we're going to pick k to be the least significant bit in which v's color and its successor's color differ. Okay, so this is how we define this k over here. All right, and then given this k, we're now going to give a new color to v. Okay, so currently its color is, let's say, C of v. And now we're going to give it a new color, C prime of v. And the C prime of v is going to be defined as 2 times k. Okay, so again, k is the least significant digit where v and its successors' colors differ in the kth bit. Okay, so C prime of v is going to be 2 times k plus the kth bit of v's current color. Okay. All right, so as an example of this, suppose that we have this situation right here. Okay, so currently all of these nodes have colors, right? And this is a valid coloring because for all pairs of nodes, for each edge, the 2 endpoints have different colors. All right, so then the first thing we're going to do is we're going to write down. So here we're listing out the color of each node. Okay, and then now we're going to convert that to its binary representation. Okay, so we're listing the nodes in the order that they appear in this cycle. Okay, and then we write out the binary representation of each node's color. And then for each pair of nodes, so for example, for let's say that v is this node with color 7 right now. Okay, we're going to look at this node and its successor node, and we're going to look for the least significant digit where their colors differ. Okay, so this is going to be in the zeroth or in the first digit. Okay, so the 0th digit. Okay, so let's call this the 0th digit, and then so this is going to be the 0th digit, like the 1, 2, and 3. Okay, yeah, so they differ in the 0th digit. So therefore, k for this node 7 here, right, is going to be 0. Okay. And then so the new color for this node 7 over here is going to be 2 times k, okay, plus its digit in the 0th digit. Its value in the 0th digit. Okay, or it's 0th digit. Okay, so which is this 1 over here. Okay, so therefore 7 is going to get a new color, which is 1. Okay, so we can look at another example. So for example, if you look at node 14 over here, okay, node 14, we're going to look at its successor, which is this node with color 2 over here. Okay, we're going to look for the least significant digit where their colors differ. And so this is going to be this 2's digit over here. Right? So k is going to be equal to 2 for this node with 14 over here. Okay. And then its new color is going to be 2 times k plus its value in the second digit, which is 1. Okay, so therefore its new color is going to be 5. All right, and so we're just going to do this for every single node. All right, you take the node, you take its successor, you look at their colors, and you find the digit where they differ. Right, there's some digit between 0 to 3 in this case. Okay, and you just take that number, multiply by 2, and then you add the kth digit to that. Okay, so now we have this following claim. So first of all, if C is a valid coloring, so if we start the round with a valid coloring, right, then the claim is that this new coloring, C prime, is also valid. Okay, so the reason this is true is because because C is a valid coloring, then this node V and its successor have different colors. Okay, and so therefore there must be some digit where their colors actually differ. Okay, so therefore this k value actually does exist. Okay, and now in order to show that the C prime is a valid coloring, let's suppose for contradiction that it's not a valid coloring. Okay, so so suppose that we have this node V and its successor U, such that with the new coloring C prime, U and V have the same color. Okay, we want to show that this is impossible. Okay, and the reason this is impossible is because so V is going to get a color which is equal to 2k plus its current color in the kth digit. Okay, for some k, right? So k is basically the digit that V and U, such that V and U's color differ. Okay, so that's going to be V's new color by definition. and then U's new color is going to be 2 times L plus its Lth bit. Okay, where L is basically, we're going to look at U and its successor, and then we're going to look at where they differ in the Lth bit. All right, so those are the new colors for U and V, and we want to make sure that they cannot be the same. Because if they are the same, right, if U and V's new colors are the same, then because these two bits here, okay, these two parts, the CU sub L and the CV sub L, okay, so these are just single bits, right? So they're either 0 or 1, okay. So therefore, if we have that C prime of V and C prime of U are equal to each other, then we have to have that L and K are equal to each other, okay? Because if L and K are not equal to each other, then since we're going to multiply L and K by 2, right? Then in this part, we're going to have the color of U and V are going to differ by at least 2. Okay, and in this part, the difference is at most 1. So if there is a difference over here, okay, if they're not equal to each other over here, then there's no way to make up for that difference using these CV and CU, using these bits over here. Okay, so it must be that L and K are equal to each other. Okay, because otherwise, U and V, C prime of U and C prime of V cannot be equal to each other. All right, so then K and L are equal to each other, but then that means that because these two things are equal, and then because L equals K, right? Then we also need to we also must have that these two bits are equal to each other. Okay, and now since we know that L equals K, then this CU sub L is simply equal to CU sub K. All right, so that means, so what this means is that the kth bit of U, right, equals the kth bit of V. All right, again, that's because C prime of V equals C prime of U, and so 2L must equal 2K, and so these two things have to be equal, and also L equals K, and so therefore we get that U and V are actually the same in their kth bit. Okay, but this is a contradiction because we define K as a bit where U and V's color actually differ. Okay, where the current color of U and the current color of V, they actually differ in the kth bit. Okay, and now if we assume this, then we must have that U and V have the same bit in the kth digit. Okay, so therefore we have that C prime of U and C prime of V are not equal to each other. Okay, and so therefore this is going to be a valid coloring. Okay, so then we're just going to take this little subroutine which starts with a valid coloring and then produces a new valid coloring, and we're going to run this over and over. Okay, so now the question is how many times do we need to run this for? Okay, so the number of times that we run this is equal to the time complexity of the algorithm. Okay, because each time we run this, we can do this in parallel for all of the nodes at the same time. Right? So in order to figure out the parallel running time for this algorithm, what we're going to do is now suppose that we're in a certain round, and let's say that the maximum number of bits used to represent any color is T. Okay, so for example, if T equals 4, okay, then all of the colors are between like 0 to 16. Or sorry, 0 to, I guess, 15, okay? Yeah, okay, so in that case, then the maximum, so we're currently using T bits to represent the colors in the current round, okay? Now let's look at how many bits we need to represent the colors in the next round. Okay. Well, in the next round, the maximum color is going to be at most 2T plus 1. Okay, because remember the way that we form the colors for the next round is that we're going to look for a digit where these two neighbors differ. Okay, where their colors differ. Okay, so that digit is going to be a number between 0 to T. Okay, because we have at most T digits here. So they differ in one of these digits between 0 to T. Okay, and then after we find that digit, we're going to multiply that by 2, and then we're going to add the kth digit in. Okay, and so that kth digit is at most 1. And so therefore, the color that we can have for the next round is going to be at most 2 times t plus 1. And in order to, so the maximum number that we need to represent for the next round, okay, so the number is the color of a node, and the maximum number we need to represent is just 2t plus 1. And so the number of bits you need to represent a number 2t plus 1 is just going to be the ceiling of log t plus 1. Okay? Okay, so yeah, so now notice that the number of bits that we're using to represent a color is going to decrease from t to log t plus 1. Okay, so for example, if in the current round, let's say that we're using 16 bits to represent the colors. Okay, so if we're using 16 bits, then we can represent any number up to like 2 to the 16th minus 1. Okay, so that's something like 65,000. Okay, so in the current round, we're using something like 65,000 colors. Okay, but then in the next round, how many bits do we need to represent a color? Well, all we need is log of t plus 1. Okay, so yeah, so log of t, so t is currently equal to 16, so 2 times log of t plus 1. Okay, so that's going to be 9 bits. Okay, so we're going from 16 bits all the way down to 9 bits. Okay, so then for 9 bits, the maximum color is going to be 2 to the 9 minus 1. Okay, so that's going to be something like 511 colors. Okay, so we've managed to decrease the number of colors from something like 65,000 to about 500 colors. Okay, and then in the next round, we're going to decrease that again. Okay, because you know, if we're currently using 9 bits to represent a color, oh, sorry, we're not using, sorry, the maximum color is going to be 2t plus 1, but the number of bits is going to be log t plus 1, so that's just 5. Okay, sorry about that. Yeah, so it's going to be log of t plus 1, so that's 5. Okay, so the number of colors we're going to use is at most 2 to the 5th minus 1. Okay, so we're only down to like 31 colors for the next round. Right, so we went from 65,000 colors down to 31 colors. Okay. So now you can see that the number of colors that we're using is decreasing very quickly. Okay. And eventually, once we get down to 3 colors, then we can stop the algorithm. And so since we can decrease the number of colors very quickly, then this means that we don't have to run this algorithm many rounds before we can stop. Okay, yeah, so now to do that analysis more rigorously, so let's define this new function, which is called this iterated log function. Okay, so this means that, so log to the log iterated I times on x, okay, simply means that you take x, and then you take its log, and then you do that I times. Okay, so you take the log of the log of the log of the log, and so on, of x. All right, so then given this iterated log function, let's define log star of x as we start with x, okay, and then we look at how many times we have to take logs until the value becomes less than or equal to 1, okay? And now this log x value, this log star value is actually very, very small, okay? So it's an increasing function in x, right? So as x gets larger, we have to take log more times. But it increases very, very slowly. Okay, so for example, even if x is something like 2 to the 65,000, okay, so x is this very, very massive number, right? Log star of x is less than or equal to 6. Okay, so if you take a number up to this big, and then if you take 6 logs, okay, then you're going to be down to like less than or equal to 1. Okay, so this is it's an increasing function, but it's a very, very slowly increasing function. Okay, and so now the claim is that this log star function, this actually gives the time complexity for the algorithm. Okay, so what we're saying is that if we have a cycle with n nodes, then in log star n number of rounds, okay, we can find a 3 coloring for all the nodes. Okay, so even if we start with like, 2 to the 65,000 number of nodes, okay, this massive, massive number of nodes, then in 6 rounds, right, because log star is 6, okay, in order of 6 rounds, we can find a 3 coloring for all the nodes. Okay, yeah, so so this is what we're going to try to show. Okay, and the reason is because what we saw was that in each round, if you start with a number that if you start with a coloring that requires t bits to represent, then in the next round, your coloring only requires order log t bits to represent, right? This is what we said, right? So we're going, currently in this round, we need t bits to represent a color, okay? And then in the next round, we only need about log t plus 1 bits to represent a color. Okay, so the number of bits we're using to represent these colors is decreasing by taking these logs. Okay, and we know that initially in the first round, if we have m processes, right, then each process, the initial color is just its ID. So therefore, the number of bits to represent the ID is just log of n, right? And so therefore, if you initially we start with log m bits to represent the colors, and then if you keep taking logs, right, because each round you reduce the number of colors that you need by this log, then in log star n number of rounds, we're going to be down to, we're going to be able to represent any color using a constant number of bits. Okay, and so this is why this algorithm is going to terminate after log star n number of rounds. Okay. Now there's this one detail that we need to look at, which is that if you keep applying the previous subroutine, okay, then once you get down to 6 colors, you actually cannot reduce the number of colors you use anymore. Okay, because suppose that you get into a round where you're using 6 colors. Okay, then you need 3 bits to represent a color, right? Because you need to represent a value between 0 to 5. Okay, so then in the next round, since you need to use 3 bits in the current round, then in the next round, the colors are going to be between 0 to 5. Okay, because the bit on which, so in the current round, the bit on which two neighbors can differ in their color, right? That's going to be a number between 0 to 2. Okay, oops. All right, and so in the next round, the maximum color that you can have is going to be 2 times 2 plus 1. Okay, so 5. Right. So therefore, in the next round, you are again going to have to use 6 colors. Okay, so once we're down to 6 colors, then the subroutine sort of doesn't work anymore. Okay, can't reduce the number of colors anymore. But we actually know that on a cycle, we need to use at most 3 colors. Okay, so now we can actually go down from 6 colors to 3 colors. And the way we do this is we're going to do like a different little subroutine. So after we get down to 6 colors, we're going to run for 3 more rounds. Okay, and in these rounds, so in the ith round, okay, we're going to take any node that's colored using color I plus 2. And then we're going to color it using the minimum possible color in 0, 1, or 2. Okay, so for example, in round 1, we're going to take any node that's colored using, so when we're starting this round, everybody is colored using colors 0 to 5. Okay, and then in round 1, we're going to take any node that's colored using 3, right? And then we're going to try to color it using the minimum possible color in 0, 1, 2. Okay, now we know that we can pick one of these colors because, if you pick one of these nodes that's color 3, right, then if it's only got 2 neighbors. Okay, so its 2 neighbors are only using 2 out of these 3 different colors. Okay, so therefore we can just give this guy with color 3, we can give him the unused color in the set. All right, and then in round 2, we're going to take any node that's colored using 4, using color 4, right? And again, you're going to look at its 2 neighbors, and you're going to pick one of the unused colors. Okay? And then you do it for the nodes colored 5. So then after you do these 3 rounds, then everybody is going to be using a color between 0 to 2. Okay, so then we have a 3 coloring. Okay, so to sum all this up, to sum up everything, what we did was we managed to 3 color all of the nodes, right? and the number of rounds we run for is, so we run for log star n number of rounds, and then we can get down to 6 colors, and then you run for 3 more rounds, and then you can get it down to 3 colors. Okay. Right, and the total amount of work that we did was n times log star n, okay, because every round, all of the n nodes are working in parallel. Now, this is actually not a work-efficient algorithm because if you do this, if you try to 3-color the ring sequentially, you can just do it in n time. Okay, so the work that you need is only n in that case. But it turns out that we can actually modify the previous algorithm so that we can produce a 3-coloring. But now we're going to take order log n time, but we're going to do linear work. Okay, and this log n time is actually enough when we try to use this coloring algorithm in a subroutine, as a subroutine in some other algorithm. Okay, because that other algorithm, so basically the other algorithm is going to work in log n time also. So therefore we don't really need for the coloring algorithm to work super fast. Okay, we don't need this log star n running time. It's okay that it just has a log n running time. Okay, but we do want to change the work so that it becomes only linear work. Okay, because the other algorithm where this coloring thing is used as a subroutine, that other algorithm has linear work. Okay, so we want to make sure the subroutine itself does not have more work than the parent algorithm. Okay, so now specifically what we're going to use this coloring algorithm for is to produce an independent set. Okay, so now if you remember from the previous lecture, when we wanted to do list ranking, in a work-efficient way, right? We actually we needed to find these independent sets, right? Because we kept on removing nodes from this independent set, and then until we got down to like a small number of nodes. Okay, and so we needed to find these independent sets quickly, and also and also using linear work. Okay, so it turns out that. So it turns out that by using coloring, then we can actually find large independent sets very quickly. Okay, so specifically, if we're given a k-coloring of a line graph, okay, so the previous algorithm worked for cycles, but it also works for line graphs. Okay, so the only difference is that you take out one edge from the cycle and you get a line graph. Okay. So suppose you're given a k-coloring of the line graph, which has n nodes, right? Then on that line graph, you can compute an independent set of size at least n divided by k, okay, of size omega of n divided by k in constant time. Okay, so if your k here is like a constant, if it's like 3, okay, then this is saying that basically you can find an independent set of size at least n over 3, okay, in constant time. Okay, so the reason this is true is because okay, so given a k-coloring, then every node has a color between 1 to k. Okay, so now in order to find this independent set, what we're going to do is to take nodes whose colors are local minima. Okay, and then we're going to take these nodes as the independent set. So as an example, suppose you have this situation over here. Okay. Now, the colors of the nodes are given by these values in the parentheses. Okay, so for example, this node 6 here has color 1, right? Node 4 has color 0, and so on. Right? And now we're going to take the values, we're going to take colors which are local minima. Okay, meaning that this color is going to be less than both neighboring colors. Okay, so for example, well, this 1 here is not a local minima, right? Because it's bigger than its neighbor, but the 0 is less than both its neighbors. Okay, so this is a local minima, so we're going to include this node in the independent set. Okay, this 2 is not a local minima, but this guy is a local minima, right? This guy's a local minima, and this guy's a local minima. Okay, so therefore we found 4 nodes who are local minima. Right, and notice that these 4 nodes, they actually do form an independent set, okay, because none of them can be neighbors of each other. Right? By the definition of an independent set is that we pick nodes who are not neighbors of each other. Right? And the reason they're not neighbors of each other is because each of these nodes is a local minima. So it's got to be less than both of its neighbors. Okay, so its color is less than both of its neighbors. So therefore, you can't have 2 neighbors who are both local minima. right? They can't both be less than each other. Okay, so therefore, these nodes that we picked out are local minima, right? And we can compute all of these local minima in constant time, right? Because every node just looks at its two neighbors and decides whether it is a local minima. Okay, all right, so now next we need to show that this set of independent nodes is quite large, okay, that we managed to pick out at least n divided by k number of these nodes, okay, or order n divided by k number of these nodes, okay. And now the reason this is true is because you know, if you take any two nodes that you selected, okay, like for example this node and that node, right? Now because they're local minima, okay, then if you look at the colors of their neighbors, okay, so suppose that you selected this node, okay, and it's got some color like this. Now if you look at the colors of its neighbors, they're first of all going to increase and then possibly decrease. Okay, so sorry. What I mean by this is suppose you take two of these nodes, U and V, that you included in the in this independent set. Okay, and now so here what I'm drawing is like the color. Okay, so so the higher up you go, the higher the color. Okay, and now because you use a minima, a local minima, right? Then its color is actually less than both its neighbors' colors. Okay, and now if you look at the neighbors' colors, right? So now if you look at two consecutive local minima, okay, then what has to happen with the colors is that they first increase, right, and then they decrease. Okay, so this is between two consecutive independent nodes that we pick. Okay, right, and so so if they first increase and then decrease, then at most there are going to be 2k minus 3 nodes between U and V. Okay, because you know, these two guys, because all of these colors are different, right? And so you know, this guy is using a color, and so here there can be at most k minus 1 other colors, okay? And then here there can be at most k minus 2 other colors in the decreasing part. So therefore, altogether there can be at most 2k minus 3 colors, 2k minus 3 nodes between U and V. Okay, because all of these nodes between U and V, they first have to increase in color. So there is at most k minus 1 of these nodes, and then they have to decrease in color. So there's at most k minus 2 of those nodes. Okay, so that means that there are not too many nodes between U and V. Okay, and because there are not too many nodes between U and V, then you know, we must be then there actually must be lots of these nodes in S. Okay, in particular, you know, since there are at most 2k minus 3 nodes between any two consecutive nodes in S, then the number of nodes in S has to be at least n divided by 2k minus 3. Okay, so then this shows that we can indeed get an independent size of size at least n divided by 2k minus 3, and you can do that in constant time. Okay, yeah, and so altogether, in order to compute an independent size of, so this k here is a constant, right? Because we show that we can actually 3-color the line graph. Okay, so we can simply treat this as a so 2 times 3 minus 3, so that's 3. Okay, right? So we can so therefore this shows that we can get an independent size of at least independent set of size at least n divided by 3. And we can do that by first coloring, right? And if we use a work efficient coloring algorithm, that's going to take us log n time, right? And order n work, right? And then we can do this this independent size computation. Okay, so altogether we get this independent set of this size in log n time and linear work. And so this is what we needed in order to run the list ranking algorithm in a work efficient fashion. Okay, yeah, so we showed that by using the subroutine, then we can actually get work efficient and logarithmic time list ranking. All right, so so the next problem we're going to look at is connected components. Okay, so in this graph, so this is a very basic algorithm in in sequential graph algorithms. And so just to remind you what this problem is, so we're given an undirected graph, okay? And then we want to partition this graph into sets of into maximal sets of connected nodes. Okay, so for example, in this graph, right, this is going to be one connected component because all of these nodes are connected to each other, right? And then this, and then this thing in the middle, right? So this is going to be another connected component, right? And then the thing on the bottom is also a connected component. Okay, so given a graph, we want to find all its connected components. Now, in a sequential setting, we would normally just solve this by like breadth first search or depth first search. Okay, and then this would take a linear time, basically, m plus n. Okay, where m is the number of edges and n is the number of vertices. However, in the PRAM setting, we can't use the BFS or DFS algorithms to find connected components. And this is because we don't have efficient algorithms, efficient PRAM algorithms to do either BFS or DFS. Okay, so the algorithms we have for BFS and DFS are either going to have a very large depth. Okay, so they could have something like linear depth. Okay, linear in the number of nodes, linear depth. Okay, or the work is going to be very high. So we don't have PRAM algorithms which both have linear work and also like a logarithmic depth. So therefore, we're not going to use BFS or DFS to solve connected components in the PRAM setting. Instead, we're going to use a technique called graph contractions. Okay, so this is actually a very widely used technique in PRAM algorithms and in general in graph algorithms. Okay, and so so I'm going to give an example of this of how we actually do graph contractions on the next page. But basically, so the contractions are going to take a set of nodes and then merge them together. Okay, so for example, we're going to take, let's just delete this. We're going to take this set of nodes, and then we're going to contract this entire graph, and we're going to form one big node out of it. Okay, so we're going to merge all 4 nodes into like one big node. Okay. Okay, so maybe, let me say this a bit differently. Okay, so actually what we're going to do is we're going to take like let's say a small set of nodes. Okay, so let's say that you take this set of nodes. Okay, and then you merge these into one big node. Okay, and then maybe you take this set of nodes, right, and then you merge these into one big node. Okay, so you're just going to take these small sets of nodes and then you're going to merge them into what we're going to call a super node. Okay, so that's like a big node that includes all of these smaller nodes that you contracted from. Okay, and so after you do this contraction on a graph, okay, we're going to end up with a bunch of these super nodes. Okay? And if we have a connected component in the original graph, then these super nodes are also going to be connected to each other. Okay, so if you look at the graph on the super nodes, okay, so not on the original nodes, but now you look at the graph on the super nodes, then this graph preserves the connectivity of the original graph. So whatever nodes were originally connected, then after you form these super nodes, right, then you have the same set of connected components. Okay, and now you can apply this technique iteratively. Okay, you can take these super nodes, and then once again, you can merge some of these super nodes together. Okay, so you get like super nodes. Okay, and then you just keep doing this process recursively. And the key point is that whenever you do this, you preserve the set of connected components. Okay, so originally, if we had 3 connected components, right, but if you do this for one round, you have a bunch of super nodes, but these super nodes also form 3 connected components. Okay, you do this again, and you get like super nodes, and these super nodes also have 3 connected components. Okay, so if you keep doing this, then eventually you're going to merge all of the nodes in each connected component. All of those nodes are going to get merged into a single like super node. Okay, so at the end of this, right, then we're for this graph, we're just going to end up with 3 super nodes. Okay, which come from merging each of these 3 connected components. So this is a basic idea for this algorithm, but there are actually many different ways that we can implement this algorithm, because it depends on how we implement this contraction operation, right? And we have different ways of implementing contraction. So today I'm going to talk about two different algorithms for connected component. Both of them do this contraction, follow this contraction idea, okay? But they actually implement the contraction step differently. Okay, so the first algorithm is going to be a randomized algorithm. Okay, so this algorithm is allowed to make some random decisions. Yeah, and we're going to see that by using randomization, we actually get a very simple algorithm. Okay, so what we're going to do is, so the randomized algorithm, basically it's going to take your initial graph, right, and then break the graph into a bunch of little star graphs. Okay, and then it's going to contract each star graph. And so what we mean by a star graph is just something that looks like this. Okay, so it's got like a center node and then a bunch of other nodes around it. Okay, yeah, so we're somehow going to take the graph and then break it into these star graphs and then contract each star graph into the center node. Okay, so like all 6 of these nodes become contracted into like a single node. All right, now to do this, what we're going to do is we're going to run a number of phases, and in each phase, we're going to do these following steps in parallel. Okay, so the first thing is that every node is going to get a random number. Okay, so it's just going to flip a coin, right? And the coin is going to produce a random result. And based on the coin flip, the node is going to choose to either be a parent node or a child node. Okay, so yeah, so if we start with this graph over here, then the first thing is that all of these nodes, they're going to flip a coin. Okay, so this is where we use the randomization, and then based on the coin flip, right? So if it's like a head, then they're going to be a parent node, and if it's tails, they're going to be a child node. Okay, so then we have, let's say, this situation over here. Okay, so then now every child node is going to point to a parent node that it's connected to. Okay, so for example, this child node, okay, it's going to point, it's got 2 neighboring parent nodes. Okay, so it's going to choose one of them. It can choose it arbitrarily. Okay, but it's going to choose one of these parent nodes, and it's going to point to that parent node. So for example, it's going to choose the 3 as a parent node, and then point to 3. Okay. Likewise, let's say this node over here. Okay, well, it's got a neighbor which is a parent node, so it's going to point to that parent node. Okay, and this node 5 over here, it's also got 2 choices, and it's going to choose arbitrarily to point to 7. Okay, so then once you do this, you see that now you have a bunch of stars. Okay, you've taken the graph and you've decomposed it. Oh, sorry. One more thing is that sometimes you have child nodes. And none of the neighbors are parents. Okay, so for example, 0 over here. Okay, it doesn't have any parents. Okay, parent neighbors. Okay, in that case, it's just gonna stay as a single node by itself. Okay, that's not a problem. Okay, it doesn't have to point to somebody. Okay, but if it has a parent, if it has a neighbor who is a parent, then it has to choose one of those neighbors, one of those parent neighbors to point to. Okay, so then after you do this, you see that the graph is going to become a set of stars. Okay, so basically the parents are going to be the centers of the stars. Okay, and the child nodes, neighboring child nodes, are going to point to the parent. Yeah, and then if you have one of these child nodes with no neighbor who's a parent, right, then it's just going to form its own star. Okay, so next we're going to do the contraction step. Okay, so the contraction is going to take each of these stars, and then it's going to contract it to the center of the star, to the parent node. Okay, so if you do that, then all 3 of these nodes are going to get contracted to this parent node over here. Okay, this 4 node over here. Okay, these 2 nodes get contracted down to the 3, right, and then these 2 nodes get contracted to the 7, and then this node just stays as a node by itself. Okay, and now if you look at the edges, right? So you have an edge from the 0 node to this sort of contracted 3 node over here, right? So we have this edge which goes from the 0 node to this cluster of 3s over here. Okay, so we're just going to denote that by this edge over here, right? We also have an edge between 0 to this 4 cluster over here, right? So we have this edge, and then we have an edge between 3 and 4. and then we have an edge between 4 and 7. Okay, we're going to remove all of these internal edges. Right? So the contraction basically is going to merge all of these nodes together, and it's also going to remove all of these edges within the star. Okay, so now we've gone from this initial graph, right? We've contracted it to the smaller graph, right? And you see that, well, the initial graph has one connected component, and the smaller graph also has one connected component. Okay? Because when you do this contraction process, you're not going to create or lose any connected components, right? You're going to exactly preserve the set of connected components. And so, so therefore, we can now take this contracted graph, and you can run this contraction process again. Okay, so again, each of these nodes is going to randomly choose to be a parent or child, right? And then the children are going to point to neighboring parents, and then we're going to get a bunch of stars, and then we're going to contract them, and then the graph gets smaller. Okay, so the graph keeps getting smaller, round by round, and eventually, because everything over here comes from one connected component, then eventually all of this is going to get contracted down to one single node. Okay, so so once it gets contracted down to that single node, then what that indicates is that everything from so that single node was formed by contracting everything in the connected component down to that single node, right? And now we want to make sure that all of the nodes in this connected component, right, they're just going to get the label of the final node. Okay, so everybody in this connected component gets the same label. And in this way, they know that all of these nodes know that they come from the same connected component. Okay, so therefore, we want to make sure that we can label all of the nodes in this connected component by the label of the final node that they all contract to. Okay, and so the way we do this is that each time we do a contraction, right, we're going to label all of the nodes that all the children get contracted into the parent, and we're going to label the children by their parent. Okay, so for example, these two nodes, right, they both become labeled 4. Okay, so we actually have 3 nodes now that become labeled 4. Right, both these guys get labeled 3, and these guys get labeled 7. Yeah, right. And then so we do this recursive process of merging nodes, right? And then eventually the recursion is going to bottom out, and then as we escape from the recursion, then each of these children nodes is going to take the node of its parent. The parent node's label might have changed. Okay, so then the children node need to take the parent's new label. So for example, if all of these nodes, okay, so currently they have different labels, right? So if eventually everything gets merged down to this 4 node, right, then what we need as the recursion returns is for this this label of 4 to get propagated to all of these other nodes. Okay, so in the end, all of the nodes in this entire component are going to be labeled 4. Okay, so now in terms of how to actually implement this, okay, so I'm going to go into a bit of details about how to implement this. So what we're going to do is we're going to use m plus m processors, where n is the number of nodes and then m is the number of edges, okay? And then, yeah, so, sorry, they should be switched. These should be V and E, okay? So in fact, we're going to have one processor for each vertex and also one processor for each edge. Okay, so we're going to call these the V processors and the E processors. Right, and the V processors are maintaining this label, right? Because eventually we want to contract everything down to one node, and we want that single node's label to get propagated to all of the other vertices. Okay, so the V processes need to keep track of the label. So each V process is attached to one of these nodes. And that the V process needs to keep track of the label for the node, okay, because that label can change over time. And then each E process is going to be assigned to one of these edges, okay, so yeah. All right, now these V and E processes, they can become inactive over time, Okay, so for example, once we contract these children nodes down to its parent, right, then we only need to keep the parent. So here we have 3 different V processes, right? But once we contract these 3 nodes down to the single 4 node, then we only need the V process for this 4 node to remain active. Okay, we don't need these other 2 children nodes to remain active. Okay, and likewise, if you contract an edge, right, then you don't need that edge process to remain active. Okay, so so the first step is for all of these nodes to decide whether they're going to be a parent or child node. Okay, so the first thing is they're going to flip a coin to decide whether they're a parent or child. And then, right, okay, and then we want to propagate the label of the parent to the children, right? And the way we do this is that, we have an E process assigned to each edge. Okay, so we're just going to have that E process read, its 2 endpoints, right? So the E process is associated with these 2 processors, right? So it's going to read the labels of these 2 processors, and it's going to check whether one processor is a parent and the other is a child. And if that's the case, it's going to set the child's ID, or the child's label, to be the parent's label. Okay, so it's going to set this to be a 4. Okay, and likewise, this guy's going to set this E is going to set this 6 to be the new label 4. Okay, so now we could have, if we look at another example here, you have like 2 E processes, okay, assigned to these 2 edges. Okay. So now this this E process over here is trying to set 2's label to a 3, okay, and then this E process over here is trying to set 2's label to a 4. Right, because 2 can either point to 3 or to 4. Okay, and in this case, we're going to have so these 2 processes are basically writing to a field that's associated with this process. Okay, they're both writing to the same field, and this guy's writing 3, and this guy's writing 4. Okay, so we have this concurrent write situation, and in this situation, we're just going to let one of these concurrent writes win. Okay, an arbitrary one of them. Okay. So either 3 or 4 can get written to this 2's label over here, right? And in this case, it so happens that 3 won. Okay, so the label 3 got written over here, so that means that 2 is now going to point to 3. Okay, but it doesn't matter which one wins. Okay, we can let an arbitrary one win. Okay, so next we're going to deactivate some of these processes because we don't need them anymore. Okay, okay. So first of all, each parent process is going to stay active. Okay, so these black node processes, they're going to stay active. Okay, and second of all, if a child process's label did not change, okay, then it's also going to stay active. Okay, so for example, this guy's label doesn't change because it didn't point to a parent. Okay, so then this guy's going to stay active. But this child node's node's label did change, so it's going to become inactive. Okay, and also for these edge processes, okay, they're going to stay active when their 2 endpoints have different labels. Okay, so for example, this edge process, okay, the endpoints have different labels. They're going to be 0 and 4. Okay, so this guy's going to stay active. But this edge process, okay, his endpoints have the same label. They're both 4. So that in that case, they're going to become inactive. Yeah. Okay, so right. Yeah, and then the active vertex and the edge processes are going to continue running the algorithm recursively. Okay, and then in the end, after the recursion returns, right, then some of these inactive edge processes, they actually need to become active again, and they need to write. They need to help propagate the labels. Okay, so for example, if all of these processes eventually got merged down to this 4 process, right, then this node 3, right, his label would have eventually changed to a 4. Okay, so when this edge process became inactive, this vertex here was still labeled as a 3, right? Because but then eventually when the recursion finishes, this 3's label might have changed to a 4. Okay, so in that case, this edge process here needs to help propagate that 4 label to this vertex. So he needs to change the 3 label to a 4. Okay, so after the recursion returns, then some of the inactive processes, edge processes, need to become active again. Okay, so and at the end of this, all of the vertex processes in the same connected component are going to have the same label. Okay, so now let's look at the running time of this algorithm. Okay, so so the key fact is that the number of active vertex processes is going to decrease by at least a quarter in expectation in each phase. Okay, and the reason this is true is because a V process is going to become inactive if it's a child process and then one of its neighbors is a parent process. Okay, in that case, it's going to point to one of its parents. Okay, it could have multiple parents being, neighbors being parents, but it's going to point. But as long as any of its neighbors are parents, then it's going to go point to one of them, and then it's going to become inactive. Okay, so so the probability that it is a child process, okay, is 1/2, right? And the probability that one of its neighbors is a parent is going to be at least 1/2. Okay, because each neighbor is going to be a parent with probability 1/2. So if you have like multiple neighbors, right, then the probability that at least one of them is a parent is going to be at least 1/2. Okay, and if both of these conditions happen, right, then this node process is going to become inactive. So therefore, the node process becomes inactive with probability at least 1/4. Okay, so that means that every round in expectation, we deactivate like a quarter of these processes. And eventually, when you're down to like one vertex process, okay, that's when your recursion ends. Okay, and so this is going to happen in log n phases, right? Because every phase you lose a quarter of your processes. So after log n phases, you're going to be down to a single process. Okay, and now and also each phase takes just constant time, right? Because all you need to do is just flip a coin and then choose one of your, and then the edge processes are going to choose which way each node process is going to point. Okay, so each phase takes constant time and it does linear work. Okay, the number of edges plus the number of vertices, that amount of work. And so therefore, the total amount of time is just going to be the number of phases times the time per phase. So that's going to be log n, right? And the total work is going to be the work per phase times log n. Okay, so this is not a work-efficient algorithm yet because in a sequential setting, you can compute connected components in just order m plus n work. Okay, and so here we're off by a factor of log n. Okay? But there are actually other work-efficient randomized connected component algorithms. Okay, so we can modify this basic idea so that we actually end up only doing linear work and also running in log time. Okay, so next we're going to look at another algorithm to compute connected components, and this algorithm is going to be deterministic. Okay, so for example, if for some reason you don't like randomized algorithms, right, then this is a deterministic algorithm to compute connected components. Okay. And it's based on basically the same idea. Okay, so it's also based on some sort of graph contractions. But as you'll see, it's going to implement these contractions in a different way. But because it's a contraction-based algorithm, it's again going to be working in phases. Okay, so each time you contract the graph in some way and you make it smaller, but you preserve the set of connected components. Okay, and you keep doing this until you're down to like one node, and then that you keep doing this until you're down to like k nodes, where k is equal to the number of connected components. Okay, so now what we're going to do in a phase is we're going to have nodes point to neighbors with lower IDs. Okay, so again, the nodes are all going to start with IDs, and each node is going to point to a neighbor with a lower ID. So for example, if you have the graph if you start with the graph on the left, right, then each neighbor is going to choose each node is going to choose some neighbor with lower ID, right? So for example, the this node 2 here is going to point to the 0, right? The 3 is going to point to the 2, right? The 4 node here has several choices. Okay, it can point to 2 or it can point to 1, and it's just going to choose one of those arbitrarily. Okay, so if you do this, if you have each node point to a neighbor with a smaller ID, then this is going to break your graph into a set of directed forests. Okay, so the forests are going to be rooted at these nodes, which are like which are local minima. Okay, which do not point to anybody else. Okay, yeah. So so here we're going to end up with like 2 of these directed forests. Okay, the 0 here is a local minima, and the 1 here is a local minima. And now we're going to contract each of these directed forests down to the root of that forest. Okay, so on the left over here, we're going to contract all of these nodes down to the 0 node. Okay, and then over here, we're going to contract all these nodes down to the 1 node. Okay, and the way we're going to do that contraction is by pointer jumping. Okay, so if you remember pointer jumping, so if you just look at the set of edges here, okay, so there's going to be a path from any node to the root of its tree that it's in, right? So there's, for example, a path from the 5 node to the 0 node, okay? And so we're just going to apply pointer jumping on this path in order to make 5 point to the 0 node. Okay, so remember that pointer jumping means that 5 is going to, 5 is currently pointing to 3. Okay, so 5 is going to look at who 3 is pointing to, right? So that's going to be 2, and then 5 is going to directly point there. Okay, and then in the next round, so now 5 is pointing to 2, and 5 is going to again look at who 2 is pointing to, which is now going to be 0, right? And so 5 is going to end up pointing at 0. Okay. Yeah, so if you and then you do this for all of the nodes in this little tree over here. Okay, so for example, 4, if it does pointer jumping, then it's also going to point at 0. Okay, so therefore, by doing this pointer jumping, we're going to have all of the nodes in each of these little trees. They're going to point to the root of that tree. Okay, and that contracts all of these nodes down to the root of the tree. And now we're going to recursively run the algorithm on this contracted graph. Okay, so in terms of how to implement this, we're again going to use m plus m processors. Okay, where n is we have m processors for the m vertices, and then we have m processors for the m edges. Now here we're going to have a small difference, which is that the vertex processors are always going to stay active. Okay, in the previous randomized algorithm, we had that these vertex processors could sometimes become inactive. Okay. But here, the vertices are always active, but the edge processors can also sometimes become inactive. Okay, just like before. Okay, now the edge processes are responsible for generating these pointers. Okay, so the first step is for each node to point to one of its lower neighbors, right? So the edge processes are responsible for setting these pointers. Okay, so for example, you have, let's say you have an edge process over here, and then you have an edge process over here, right? And so this guy on the bottom, right, he's trying to make 4 point to the 1. And this guy, well, first of all, this edge over here, he's going to check his 2 endpoints, and he's going to try to make, set the direction to point to the smaller direction, okay, to the smaller node, right? And then this edge process is trying to make 4 point to the 2, right? So both of these processes are writing to some sort of field that's in this, that's stored by this 4 node over here, okay? And so they're doing a concurrent write, and it doesn't matter which one of these wins. Okay, so in this case, the process writing a 2, he won. All right, but anyways, so these edge processes are first of all going to check this edge UV, and then it's going to set, it's going to try to point this edge in the direction of the smaller node. Okay, and then after we form these pointers, right, then we can do the pointer jumping. Okay, and the V processes are responsible for the pointer jumping. Okay, so they're going to do the pointer jumping, and yeah, so so for example, this 5. Okay, when it does the pointer jumping, it's going to set its label. So initially it was it had a label of 5. Okay, and it's going to take the label of whoever it points to. Okay, so this 5 here is going to change its because it's initially pointing to 3. It's going to change its label to 3. Okay, but then after it does pointer jumping once, it's going to point to 2. So then it's going to set its label to 2. And then eventually it's going to point to 0. So then it's going to set its label to 0. Okay, so whoever it points to, it's going to set its label to that guy. Okay, and the 0 node, right? He doesn't point to anyone, so he never changes his label. Okay, so everybody else eventually gets changes their. Everybody else in this tree, after doing the pointer jumping, eventually is going to set their label to 0. Okay, and now we're going to deactivate some of these edge processes, okay? Because basically the edges which are in each tree, right, we don't need those anymore. But we do need the edges which go between two of these trees, okay? So we need, for example, this edge process and this one, and that one. We need those to stay active, okay? Right, and so what's going to happen after you run one round of this is all of these nodes are going to have now 0 labels, right? And then this node is going to have a 1 label, right? Because he's in the 1 component, okay? And so now you have so now you have a bunch of these edges, and each of them is pointing from the 0 to the 1, right? And so all of them are going to be setting these directions. So they're basically going to set the direction in the, they're going to set the edge's direction to point to the smaller label, right? So they're going to set in these directions. And then after that, all of these nodes in here, right? So we have 2 nodes in here, they're going to do the pointer jumping, okay? And then when they do the pointer jumping, they're going to find that they point to the 0, and so they're going to change their labels to 0s. Okay, so eventually all of these nodes are going to change their pointers, their labels to 0s. Right, okay, so that's the algorithm. Now, there's one problem with this algorithm because, so currently we're always having the nodes point from like large values to small values. And it turns out that if you run this algorithm, then there's actually these pathological cases where the algorithm is very slow, okay, where it takes linear time to complete. Okay? So our goal is for this algorithm to terminate in something like logarithmic time. But in some situations, it actually takes linear time. And so an example of this would be this graph, right? So here, these are the initial labels of the nodes. Okay, so we have one node with the maximum label 8, right? And so, so what's going to happen is that he's going to set his label to point to one of his neighbors, okay? And he can choose one of the neighbors arbitrarily, okay? But none of these neighboring nodes, none of them are going to point to the center, right? Because they're all less than the center, okay? So the center is going to point to one of the outlying nodes, and so suppose it points to 7, okay? Then its label is going to become 7. Okay, but now, again, this node in the middle is the largest, right? So none of these outside nodes are going to point to it, and this middle node is going to point to one of its neighbors. Okay, so let's say that it points to 6. Okay, so then its label is going to become a 6, right? And then on the next round, it might point to the 5, right? And then the 4, and so on. Okay, so in this graph, it can take up to like order n time before this terminates. Okay. However, the observation here is that this only happened because we're making these big nodes point to the small nodes. Okay. If we reverse the directions so that we made these small nodes point to the big nodes, okay, then this graph would actually terminate in just constant time, right? Because if we make the small nodes point to the big nodes, then everybody would point to the center, right? And then everybody would just get contracted to the center, and they would get an ID of 8 right away. Okay, one step. So, we're going to make use of this observation, and what we'll do is that in each phase, we're going to run 2 rounds. Okay, in the first round, we're going to have nodes point to lower neighbors. Okay, so just like over here, we have 8 point to one of its lower neighbors. Okay, but maybe that's doesn't work well, right? Because in this situation, it takes a long time for this to finish. Okay. So therefore, in this phase, in the second round of the phase, we're going to have nodes point to their higher neighbors. Okay, and it turns out that in one of these 2 rounds, we're going to have at least n over 2 nodes can be contracted. Okay, so so when you point to the lower neighbors, right, then we look at how many nodes can get contracted. So in this case, there's only 1 node that can get contracted, right? There's only the 7 node that can get contracted. Okay, and then we try the other case where you point to higher neighbors, and then you see that you're going to get 8 nodes which can be contracted. Okay, and so for this phase, we're just going to pick whichever round lets us contract more nodes. Okay, so in this case, we're going to pick the point to bigger neighbors round. And the claim is that in one of these rounds, at least half of your nodes are going to get contracted. Okay, and the reason is that suppose you have a node V, okay, and suppose it doesn't point to any neighbor in the high to low round, okay, where high nodes point to low neighbors, okay. So if it doesn't point to any neighbor, okay, then it must be smaller than all of its neighbors, right? Because if it's bigger than any of its neighbors, then it would point to at least one of the neighbors it's bigger than. Okay, so the fact that it doesn't point to any neighbor, right, means that it's got to be smaller than all its neighbors. Okay, so for example, this 1 here, right, it doesn't point to anyone because it's smaller than its neighbors. Okay. But if it's smaller than all its neighbors, then in the low to high round, right, then because it's smaller than its neighbors, then it's going to point to some neighbor in the low to high round. Okay. All right, so either in the high to low round, it's going to point to someone, or in the low to high round, the node is going to point to someone. And as long as it points to someone, then it's going to get contracted, right? And so therefore, in one of these 2 rounds, so every node is going to point to someone in one of these 2 rounds, and so in one of these 2 rounds, we can contract at least half of the nodes. Okay, and so because we can contract half the nodes each time, then this algorithm is going to terminate with 1 node in logarithmic number of rounds. Okay, and so to look at the amount of work, well, each round is going to do pointer jumping. Okay, so the pointer jumping is going to take log n time. And also it's going to do n log n work. Okay, so therefore, for this algorithm, currently the time complexity is going to be log squared. So the time complexity is log squared, and the work is going to be log n phases times this much work per phase. So it's going to be this is the total work. Okay, so right. Okay, so then the final algorithm we're going to look at is for minimum spanning tree. Okay, so remember that for a minimum spanning tree, we're given a undirected graph with edge weights. Okay, and we're trying to find a tree which goes through all of the nodes, right, and which has the smallest total weight. Okay, so for example, in this in this graph over here, right, the MST is going to be all of these thick edges. So among all possible trees that go through all of the nodes, this tree has the smallest total weight. Okay, so if we're in the sequential setting, then we can actually solve this in m plus n log n time, okay, using like Prim's algorithm or Kruskos algorithm. Okay, so now we're going to try to do this in the PRAM setting. And we're going to rely on one key property of minimum spanning trees, which is that if you take any set of nodes W, okay, then then if you look at all of the edges which come out of W and which go to nodes which are not in W, okay, then the minimum cost edge among that set has to be in the MST. Okay, so for example, if you take W to be this set, okay, then the edges which come out of W and go to other nodes, right, are this edge, this edge, this edge, and then this edge. Okay, and what this property says is that if you look at these four edges, then the minimum cost the minimum cost edge within the set has to be in the MST. Okay, so the minimum cost edge would be this one, right, and this is indeed in the MST. Okay, and likewise, you can take some other you can cut this some other way. So now you can say this is W, right? So then the edges which come out of this are these three edges, right? And you see that the minimum cost edge, which are these two cost 2 edges. Well, in this case, all three edges are in this one. Okay, so maybe let's take a different example. Okay, so well, if you take yeah, so all of these go through too many edges. Yeah, okay. So if we take this, okay, so this is our W over here, right? Then the edges which are cut by this W are this edge, this one, and then that one. Okay, and so the minimum cost edges are these 4 edges, right? And then one of these at least has to be in the MST. Okay, so this is the yeah, and so if you apply this to a single vertex, V, okay, then what this is saying is that for the single vertex, the minimum edge, the minimum cost edge coming out of V has to be in the MST. Okay, so for example, if you take I don't know, like this node, okay, right, then it's got 2 outgoing edges, and so the smaller one has to be in the MST. Okay. Or if you take, if you take this node, okay, it's got 3 outgoing edges, right? So the smallest, so the cheapest edge has to be in the MST, right? This one. Okay, so then we're going to use this idea, and then we're going to create a parallel MST algorithm, and it's going to work similarly to the previous randomized parallel algorithm for connected components. Okay, so what we're going to do is, so we start with this weighted graph over here, okay? And just like the connected component randomized algorithm, we're first of all going to have each node randomly choose to be a parent or child node. Okay, so yeah, so these white nodes here are the child nodes, and the parent nodes are the black nodes. Okay, and now for each child node, it's going to look at its minimum weight outgoing edge. Okay, so this child node has a bunch of neighbors, and it's got like edges to all these neighbors, and it's going to look for the cheapest edge to any of its neighbors. Okay, and then let's call that UV. Okay, so so UV is the cheapest edge going out of U, and then U is going to look to see whether V is a parent. Okay, if V is a parent, then U is going to point to V. Okay, if V is not a parent, then U is just going to it doesn't do anything. Okay, so for example, here, we have a bunch of these. So these these white nodes are the children, right? And so for each of these children nodes, it's going to look at its outgoing edges, right? So for example, the 0 guy is going to look at these 2 edges, right? And the cheapest one is going to be this 9 edge, and it's going to check whether this the other node on the 9 edge is a parent. Okay, so it is a parent. So in this case, it's going to point to that parent. Okay. Let's see. So this, let's see. So this node, yeah. So if you take this 3 node, okay. Oh, right. So this is a parent. Let's see. So all of these are, yeah. Okay. So yeah, in this case, all of them, all of these children nodes are going to point to someone. Okay. But it is possible that, if you look at your cheapest outgoing edge, right, then the other endpoint is not a parent. Okay, so in that case, U is not going to point to V. Okay, but anyways, so then we form these pointers, and these pointers again are going to create a set of stars. okay? And the parent nodes are going to be the centers of the stars. And so once again, we're going to contract each star to the parent, okay? And so that's going to form this situation over here, right, where we have these 3 parents, and then we contract we contract each of these stars down to the parent, okay? And then when you do that, you're gonna you have edges between these different parents, okay? And you could have multiple edges between the parents, and we're gonna keep all of these multiple edges. Okay, so for example, you know, these things are going to get contracted down to this 4 node over here, right? But we have 2 edges between these, you know, this 3 component here and the 3 star and the 4 star, and we're going to keep both of these edges. Okay, and then over here we have 3 of these edges. Okay, we're going to keep all 3 of them, and then we're going to do the same thing. So we're going to again have nodes choose to be parents or children, right? And then the children are going to take the cheapest outgoing edge. So it's going to take the 15, right? And then this, so this child is going to take the 15 edge, and this child is going to take the 14 edge, right? And then they're going to see whether the endpoint is a parent. And in this case, it is a parent. And then so they're going to contract down to the parent. Okay? So then each time we selected some of these edges to contract along, right? So each time we selected these edges, okay, and then we later on we selected the 15 and the 14 edges. So we selected this edge, and the 14 edge is where? Okay, it's over here, right? Okay, so all of these edges that we selected, right, at any level of the recursion. So if we take all of those edges together, okay, that is going to be an MST. Okay, so that is the minimum spanning tree. Okay, so ultimately we have this as our MST. Now, one thing is that it's a little bit tricky to find what is the minimum weight outgoing edge, okay? Because you know, you could have a node with many outgoing edges. So for example, this node, okay, he's got 4 outgoing edges, right? So so we don't want to have like a single process check all of these outgoing edges and then find the minimum among that, because that's going to take you know, if you have k neighbors here, that's going to take you know, order k time. Okay, we want to do this in constant time. And so the way you can do this in constant time is that we're going to assign 1 process per edge. Okay, so we're going to have, so just like before, these edges are going to be assigned processors, right? So we have like 4 processors for these 4 edges, right? And these 4 processors are going to write their the weight of this edge to this node 2 over here. Okay, and we're going to assume that we have this minimum priority CRCW model, where if you know, multiple values write to the multiple processes write to the same location, then we're going to assume that the minimum value wins. Okay, so in this case, the guy writing 8, he's going to win. Okay, so he's going to make 2 point in this direction. Okay, so the last thing is we're going to analyze the complexity of this algorithm. So this is basically the same as the connected component algorithm, okay? Because again, you can show that with at least, again, you can show that in each phase, at least 1/4 of the vertex processes become inactive, okay? Or you're going to contract out at least 1/4 of the nodes each time, okay? And the reason is that, you know, if you take any node U, right, then you know, it's got some minimum weight outgoing edge, right? So U is just going to check whether along this edge whether V is a parent or not, okay? And so there's a 1/4 probability. There's a 1/4 probability that U himself is a child, and along this edge that V is a parent, okay? And if that happens, then U will be contracted out. Okay, so that means that in each round, about you have 1/4 of your nodes in expectation are going to get contracted out. And so that means that after log n phases, we're going to be just left with a single node, right? And then we can get our MST just by sort of you know, bottoming out from that recursion and then looking at all of the edges that we used during the recursive process. Okay, and then as I mentioned, when you in each round, you need for each node to find its minimum outgoing edge, right? Minimum cost outgoing edge, its cheapest edge. Okay, and by having all of these processors, by having this min priority CRCW model, then we can actually find the cheapest edge in constant time. Okay, so therefore the total running time for this algorithm is going to be log n, right? And the amount of work is, well, there's linear work in each round, so the total work is going to be n plus n times log n.